Hello friends, welcome to my YouTube channel. Today we are going to discuss oscillators. Oscillators are the circuit which generates waveform for you. The type of waveform could be sinusoidal, square wave, triangular or pulses. And these waveforms are used in communication such as radio communication, television, measuring equipments or other forms of communication. Now, oscillator circuit consists of two things, two blocks. One is and other one is the feedback network. Now, part of our output is given to the feedback network, and then feedback signal is mixed with the input signal. Now, let's see how it works. Necessary condition for oscillations, which is also known as a Barkhausen's criteria. When I look at this block over here, V in at this point, V in is Vs plus Vf. Vs is this, Vf being a positive feedback, both of them will add up. So V in is Vs plus Vf. Now I can replace V in by Vo upon A and Vf by beta into Vo, because A is a gain of amplifier, which is V out by V in. Beta is gain of feedback network, Vf by Vo. So from there you replace these values, solve it, take all Vos on one side. When you solve this, you will get Vo by Vs is equal to A upon 1 minus A beta. Now for oscillator, external inputs are not there, so this Vs term over here tends to 0. So when Vs is 0 in this equation, left hand side is 0, denominator of left hand side is 0, so this right hand side denominator, which is 1 minus A beta, must be 0. Therefore A into beta is 1. When I write it in polar form, I see A into beta is 1 0 degree or 1 in 360 degree. From here I get two conditions, that total phase shift. First condition, total phase shift around the loop must be 0 degree or 360 degree, and total gain must be unity. If it is less than unity, you will get oscillations like this, where output will amplitude of output will go on decreasing. So such conditions are known as damped oscillations. Otherwise, if A into beta is greater than 1, you will get overshoot. So to get a sustained oscillation, A into beta must be equal to 1. Practically, we take A into beta slightly greater than 1. Now LC oscillators are one in which feedback circuit will consist of inductor and capacitor. So this is the block diagram of LC oscillators. Here I am using inverting amplifier and feedback network, which consists of three terms, Z1, Z2, Z3. All three of them can be inductor or capacitor. Now let's derive the condition for oscillations. Here Z can be J into X1, J into X2 or J into X3, that is the value of Z1, Z2. Now when there is no feedback means Vf over here is 0. So when Vf is 0, I can say these two, that is Z3 and Z1, are in series, and this series combination over here, they are in series circuit, and that series is in parallel with Z2. So I can say load to my amplifier is this series combination of Z1 and Z3 parallel with Z2. Now if I consider a feedback condition, Vf voltage, to find VF, let's apply voltage divider rule here. VF is Z1 upon Z3 plus Z1 into VO. This negative sign over here is due to 180-degree phase shift. 180-degree phase shift provided by inverting amplifier. So that's why we are taking minus here. So minus sign. Now from here I get VF by VO, which is beta, as minus of Z1, Z2 and Z3. This is my equation number 1. Now let's go back to this diagram here. This is inverting amplifier here. Now amplifiers can be replaced by its equivalent circuit. So in this diagram over here, this is the output side of amplifier. This is output impedance ZO. This is the gain AV into VI, output circuit of amplifier. I hope you remember amplifier circuit, which is like amplifier, equivalent circuit of amplifier. This is the voltage. Recall the equivalent circuit of op-amp like this, right? This is VI, high input impedance, and this is RO, this is ZI, and so on. So this is your equivalent circuit of op-amp. So I'm taking only this part and connected to load over here. Now when I solve this, I get VO as ZL, that is load, this is load here, load plus RO into entire voltage. Now solving this, you will get a new term which is AVL, volt, gain with load, and which is AV, this is gain without load. Please don't get confused. AVL is gain with load and AV is gain without load, or feedback also you can say. So I'll get a value of AVL over here. This is my equation number 2. Now I multiply equation 1 and 2, so I'll get AVL into beta. I solve these two equations, multiply them, solve them, and replace it by imaginary term. Z1 is this J into x1, J into x2, J into x3. Then I get AV into beta. This is important. AV into beta in terms of a real and imaginary part. This is my imaginary term and remaining is real part, imaginary. Now for oscillator, you see imaginary part must be 0. So I'll replace this imaginary part to be 0 over here. Now I know RO cannot be 0, so x1 plus x2 plus x3 has to be 0. This is my condition number 3. Why 3? First two conditions are Barkhausen's criteria. One related to phase shift, other one is related to this amplitude. These two gives you first 0 degree or 360 degree. These are first two condition. Third condition is that x1 plus x2 plus x3 must be 0. And when imaginary part in this equation over here, when imaginary part is 0, the real part is given by this. This is your real part. When I solve this part, put value of x1 plus x2, x1 plus x3. This is x1 plus x3. This is x3. There is a correction. This is x3. x3 as minus x2. So when you do that, you will get this minus gain. You write a mod of gain, so you get this condition. And for stability, AV into beta must be 1. So you'll get AV, this right hand side, AV into Z1, x1 by x2 must be greater than 1. So sine of this indicates that sine of x1 and x2 must be same. That means both of them, x1 and x2, can be either inductors or capacitors. When both of them are inductor, x1 and x2 are inductors, x3 is opposite, capacitor. It is known as Hartley's oscillator. When x1 and x2 are capacitors, and in that case x3 is inductor. That is known as Colpitt's oscillator. So there are basically two circuits we are going to discuss. One is Hartley, other one is Colpitt oscillator. Just remember this condition again, that you derive the condition, this expression AVL into beta. In this entire derivation will give you two conditions. First condition, imaginary is 0, so you will get this one, this part you will get. Second, when imaginary is 0, you will solve real part, and when you solve real part, you will get this condition, AV into x1 by x2 must be greater than 1. This gives you second condition, that x1 and x2 must be of same type, that is either inductor or capacitor. When both of them are inductors, Hartley, and both of them are capacitor, is Colpitt. Now let's go to the circuit. First is Hartley oscillator. Here we are going to design Hartley's oscillator using both this type of amplifier, op-amp as well as BJT. So this is op-amp in inverting configuration, and this is CE amplifier. You are aware of both the circuits. Here this look at the feedback. In two inductors, one capacitor, so it is Hartley. Two feedback network is same in both. Only thing that changes is an inverting amplifier. It could be inverting using op-amp or CE amplifier. Now from this circuit, just use your condition number 3. Condition number 3 was x1 plus x2 plus x3 is 0, and put the value of x1 here is inductor, and x3 is capacitive. Solve them, so we'll get a frequency of oscillation. F0 is 1 upon 2 pi root of LT into C, where LT is summation of L1 and L2. Now similarly, let's see Colpitt oscillator. Again, inverting amplifier, op-amp in inverting configuration, or CE amplifier. Both of them provide 180 degree phase shift, and your this feedback network will provide 180. Now again look at the same condition. Condition 3, you know x1 plus x2 plus x3 is 0. In this case x1 is capacitive, x2 is capacitive, and 3 is inductive. So solve that, take a equivalent, and you will get a frequency of oscillation for Colpitt oscillator. Now these derivations are important, plus if you are asked to explain the working, what you say, how you can go about is, this is inverting amplifier, right? So this inverting provides the 180 degree phase shift. Same is the case with CE amplifier also. CE amplifier also provides 180 degree phase shift. This feedback network will provide 180 degree phase shift. So 180 plus 180 plus 180, phase shift of 360 degree. Barkhausen's criteria is fulfilled. Gain criteria can be fulfilled by selecting this RF as a potentiometer, or even RC can be taken as a potentiometer to have second criteria. This is A into beta greater than or equal to 1. Thank you.